Yes. Okay. So we were talking about that approximation ratio and how these approximation algorithms are useful. So let us try to solve, okay, minimum vertex cover problem, okay, problem using randomized way. Okay, so randomization is one of the way to solve the NP-hard problems. So MVC, I write MVC for that minimum vertex cover problem. It is actually a hard problem because as the input size increases, it is difficult to solve. Okay, uh, exactly, optimally. That is with the minimum number of vertices. Okay, as you define, what is a minimum vertex cover? So it is a subset of vertices V dash such that if you have a u comma v as an edge, okay, so at least one, so either u or v or both, okay, that would be a part of vertex cover, and this should be true for every edge. Okay, this should be true for every edge, and minimum number of vertices you want. So size of a vertex cover is the number of vertices in that. So let us see the uh, okay, before starting, let me ask you, if you are given this problem to solve approximately, what would be your first idea, okay, to solve this, right? I don't want exact answer. I mean, how to solve that minimum vertex cover? Given a graph, I want to find a vertex cover. Okay, which vertex you will select first? Which vertex you will select first? Source means there is nothing like source. It's a graph, right? Anyone, okay. Anyone means randomly, completely randomly. Okay. Deep says, okay, fine. Any other thought? Preet is saying one by one and find out whether it covers all edges of the graph. Okay. Sagar is very correct. This would be a first greedy thought that can come in our mind. Let me take a vertex with highest degree. So maximum number of edges would be covered. Isn't it? Others, do you agree or not? This would be very good one. Yes. Yes, this is, so that is a greedy one. What Sagar has thought, that is also one idea. That is a greedy one. That is very good idea. Okay. So select a vertex which has the highest degree and put it in the answer. Okay. Then what should we do, Sagar? Yes, that is correct. You selected one vertex with the highest degree. So I should not keep that again. Okay. I mean, I should not keep that vertex again coming. And so what I will do, I will change the graph. So I will delete that vertex and all the edges associated with that, I will delete from the graph. And I will create a new graph. And that in a new graph, you again apply the same process. Select a vertex with highest degree. Yes. Yes. Yes or no, Sagar? Is this not like a recursion, but repetition rather? Okay. So, so that would be a greedy idea. Okay, but we will see there is some limitation of this method. Okay. So let us, so this is not a random way. Do you agree or not? This is not a random way. You are selecting purposefully one vertex which has a highest degree right now. So means that's a deterministic. It's not a random way, right? So this is a greedy way. What Sagar says, that way is also correct. It's a greedy way. What I am going to start first is a random way. So what I will do, I will randomly select any age. I will randomly select any age. Age, so it has two endpoints, u comma v. graph is undirected. I assume that, right? So I randomly select any edge u comma v from the given graph. Okay. Then what should I do? Any idea? Randomly select any edge, right? No criteria. So I fixed it. Okay. And what I do is I add both u and v in the vertex cover. So initially vertex cover is empty set. I randomly select any edge and I add both the endpoints of that edge to the answer. Okay. Now you tell me the next step. What should be the next step? Rather than I am telling, you should tell me. It's not that tough, right? I randomly select any edge, means any arbitrary edge, take its two endpoints, put it in the solution. So you and we both are the part of vertex cover. What should I delete? Should I delete anything from the graph? Yes. 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 No. So that combine that one approach is okay, but Yash, what says is delete all edges which is connected with that vertices. Very correct. So delete. So this is called incident, right? Yes, the edges which are connected with either u or v, right? You delete all them because at least one endpoint should be there, and we have u and v both. So wherever u is one endpoint, delete all such edges. Wherever v is one endpoint, delete all such edges. Create a graph, okay, new graph, and do this process. How many times we have to repeat this process? Again, same, again, same. Till what? Yes, there should be some edge, na? Yes, yes, very correct. Until all edges are deleted. Very correct. So this is a randomized way. Remember what you told me is a randomized way of vertex cover because we select edges randomly. Okay, let us see. So this is the first way. So approximate vertex cover, it's the name of an algorithm. Sorry. Okay, what is that idea? So initially, C is our answer. Solution. C is our approximate answer. So it is empty set initially. I use E dash is G dot E. So it's a set of edges. I copy the set of edges. Okay. And while that set of edges is not empty, that you told me, right? You have to repeat it until there are edges. So when there are edges, you pick arbitrary any edge. So what I do, I pick arbitrary means randomly any edge of E dash. Okay? E dash is nothing but the edges, right? You take edges, put both the endpoints of the edges in C, right? And then as we discussed, remove from E dash every edge incident with either E, incident on either U or V. Okay. And repeat this process until this is empty set. When it becomes empty set, come out and return C. Okay. So you see in every iteration, there are two vertices which will get added. In one iteration, u comma v means two vertices will be in the solution. Next iteration, two more. So 2, 4, 6. So vertex cover will be of even size. There will be even number of vertices in the vertex cover. And finally, whatever is there, you return C. Okay? So this would be one idea. Let us see how good this idea is. Let us see some examples first. Find approximation ratio so that it would be very clear. Okay, you tell me in this graph, it's not a big graph, only 7 vertices are there, few edges are there. Can you tell me what is optimal minimum minimum vertex cover? It's a small graph, so you can do it manually, right? What is the size of minimum vertex cover? You can start from 1. 1 size is not possible, then that way, right? Is 3, 3, right? Okay, one. What if odd number of vertices are there? Okay, vertices are there. That doesn't matter. Harsh, graph could be anything. What I am saying is, in answer, it should be C, the set of vertices in approximate answer. It takes 2 vertices at a time, right? And this we proceed till edges are not empty. So if there are, let's say, 5 vertices, there will be a one point of time, there will be one vertex left, but all edges are covered. So you will not proceed in the iteration. Okay. Okay, so it's not nothing to do with the graph. Okay, graph could be any with even odd, doesn't matter. I am saying just that this C would have even number of vertices. Okay, yes, the answer is correct. Do you agree with Shail, Kushal, Harsh? Yes, others? Yes, B, E, D. Okay, B, E, D. So if you take B, this edge is not required, this edge is not required. If you take E, this is not required. And if you take D, this is covered. So yes, so size 2 cover is not possible. So minimum size cover is 3. Okay, so as you mentioned, so this is optimal answer. So remember this is C star. C star is what? As you mentioned, B, E, D or B, D, E, whatever. Okay, and what is the size of C star? So we generally write the size of C star, right? Because that matters. How many vertices? It's 3. So there are 3 vertices in an optimal answer. Definitely, we will not get a 3 in approximate answer because 3 is never possible via this method. Okay. So what I will do, C is equal to empty set. So let me take one age. So let us take this algorithm. So let us take any arbitrary age. Let me take PC. So I have taken this B and C. Which edges I should delete? If I take BC, I should delete this, and this. That is AB, EC, and CD. That I should delete. Right? So BC are there. So once I take a BC, I should remove from the graph every edge incident. So in addition to BC, I have to delete this. So that's why I've shown using that dotted way, right? BA, C, and CD. Okay, those are dotted, right? In addition to BC, remember BC is not going to come again, right? So now my graph is just this one. From this graph, you have to select again arbitrary edge because set of edges are not empty. So let us take EF. You can take any, okay? EF. Now, if you take EF, okay, this edges will not be there, okay? And add EF in an answer. So earlier it was BC, now EF, so it is BCEF, okay? And now still this is one edge left, so I have to compulsory take that DG, and then you see the entire graph, all edges were removed, so there are no edges left to cover. So which means algorithm terminates, but there are 6 vertices, B, C, E, F, D, G. Okay, so if you go like this, okay, there are 6 vertices, B, C, E, F, D, G. So this gave me 6, so size of C will be 6. So what is an approximation ratio? Just for this example, approximation ratio is what? 2, very correct. How? 6 by 3, right? 3 was an optimal answer, 6 was an approximate answer, so 6 by 3 is 2, right? Let me give you another example, okay? So as you noticed, it's 2, right? Okay, what is optimal answer for this graph? You see in the red color. This type of graph is called a star graph. It's a star topology of the network. Okay, so yes, very correct. Because if you just take 6, the vertex number 6, every edge would be covered. The optimal answer is 6. But you see, if you apply our algorithm, if you select any edge arbitrarily, let me take any edge like 1, 6 arbitrarily, then you will delete everything, right? But there will be two endpoints, 1 and 6, which will come in an answer. Okay, because at least 2 endpoints of every edge will come in approximate vertex cover. So that would having 2 vertices. Any edge if you select 1, 6, it would be 2. So again, what is an approximation ratio? So 2. Yes, it's 2. So yeah. So now you see this graph. It's not that always it will be 2. It could be 2 or less than 2. That is what I want to show by examples. Then we will definitely prove that. Okay. So this, we take small examples. Okay. That's why we can compare. 1000 vertex graph. We can't do these methods manually, right? So 1, 2, 3, 4. Okay. What is an optimal vertex cover? If you take 1 and 3, all edges are covered. Okay, 1 and 3, all edges are covered. That would be optimal vertex cover of size 2. But if you select, if you use this randomized algorithm, okay, select 1, 2, you use 1, 2, and delete other 1, 4, 2, 3, delete. And then you take 2, 3, 4, because that's just edge left. So cost of approximate solution, there are 4 vertices. Optimal solution, 2 vertices. Again, the ratio is 2. Okay. The last example I am taking. Here, actually, there are 2 vertices in optimal answer, right? Because you have to take 1 or 2 or 2, 3 or 1, 3, anything. That would be optimal answer. Just one vertex will not cover every edge. It's a triangle graph, right? And so there are 2 vertices. And in using algorithm also, if you see, you pick this edge 1, 2, and remaining edges will be discarded. Okay, so there both are equal, right? Both are equal. So what is an approximation ratio? 1. Are you getting me? Yes. So approximation ratio here is 1, because the optimal answer is also this and exact answer is also this. But this is for this example, this kind of graph. Assuming this graph, you have 1. So in general, what you say? In general, what you say? From this, just an observation, from just the data. Yes, it could be 2 or less than 2. Can I say or not? Yes. Others agree? Keval, Yash, others? Yes. So, yes, the approximation ratio could be maximum 2 or it could be less than. Okay. And so, this is the thing. But you will say this is just by an examples, various examples. Okay. So let me prove this fact. Okay. That this is indeed at most 2. Now, okay, what would be the running time? So the theorem says in a Foreman book that prove that approximate vertex cover is a polynomial time algorithm. Okay, this is very important. Don't forget, this runs in polynomial time with 2 approximation ratio. Okay, it runs in polynomial time. You see this algorithm. How many times this while loop will run? So maximum number of edges time until number of edges becomes empty. Okay, this, so number of edges, which is polynomial in nature, right? That size of a graph. Okay, so this is definitely and then removing the edges and all those things are constant time operation. I mean, for one iteration. So for e iterations, if you have e is the time. So I mean, selection of age, it's a random thing. One time if you do, it's a constant time operation. Adding that this is one time if you do, it's a constant time operation. So I mean, you have to basically traverse a graph and do something on graph, delete and everything. So which depends on the size of the graph. Okay. So which means this can easily be implemented using a time v plus e if you use adjacency list. I don't go in details of this because you know from breadth first search, depth first search that if you use a matrix, it would be a quadratic time v square, okay, for traversing a graph. I use adjacency list then v plus e, which both v and e are the size of the graph, so which means it's a algorithm which runs in polynomial time. Because all the steps within the while loop takes a constant time, and while loop runs maximum ages number of until ages becomes empty. So this is a polynomial. So there is some certain number of steps which depend on original number of ages. Everyone agrees that this runs in polynomial time? Janil, Keval, Shail, Harsh? Yes, agree. Okay, so that was the first point. Now the second point. Second point is I want to prove that ratio is 2, ratio is equal to 2. Okay, let us take that. Okay, so now please pay attention. So we are proving this fact that it is indeed a 2 approximation algorithm. And now you see, we will not consider any graph in proof. I'll talk in general, right? And Priyank, please focus that your question will also be answered. I don't know the optimal solution for a graph. I don't consider 5 vertices, 3 edges graph, not like that. V vertices, E edges. Okay, any graph. Okay, and let me give you a proof. First, let me give you the notations. So capital A, let capital A, what it denote? It denotes the set of edges. Capital A denotes the set of edges that line 4 of the algorithm picks. What is the line 4 of the algorithm? The random one. Okay. Let u comma v be the arbitrary edge. So that line 4 picks set of edges that, so it's a set. Whose set? It's edges set. So the elements of A would be edges. Okay, u comma v, like that. 1 comma 2, 2 comma 3, like that. But you see, okay, can you some property about A? A is a set of edges picked by algorithm line number 4. That is which I told you. Can you tell me some property about A? Which kind of elements? Elements of this set are edges itself. Can you relate the edges which are chosen by this algorithm, or which type of edges will be there? Any property? Let's say first time I chose 1 comma 2. Let's say. Okay. Second time, is it possible to choose 2 comma 4? Is it possible? If first time I chose 1 comma, no. Why no? Because, why no? Because you remove all the incident edges, either 1 or on 2, which means every edge that you select, no element will share any common point. Am I saying true or not? No element of set A will, distinct is fine, but not even sharing the common point. Okay, yes, yeah, because we delete the incident edges. Okay, we delete what? Incident edges. The appropriate term should be incident edges to a vertex. Okay, okay, no, yes, no adjacent vertices will be there. So yes, so so that would be So in order to cover the edges in A, any vertex cover, in particular an optimal cover C star. So I will denote C star means optimal cover, minimum cover. And you see, for C star also, what is the criteria? That must include at least one endpoint of each edge in A. So A is what? Algorithm chosen edges. Set of edges chosen by algorithm. That is capital A. What is C star? Optimal answer. But C star also should satisfy everything, right? So C star is also include. C star is a set of vertices. Remember this difference. C star is what? A set of vertices. Okay, but it's a minimal set of vertices. It's an optimal answer. Okay, that's the difference. But A is a set of edges. Remember, it's a set of edges. And you see, no two edges in A share a common endpoint because once an edge is picked, all incident edges are removed. Okay, now compare the size of optimal answer and the size of set of edges. So A, the size, so C star means number of elements in optimal vertex cover. Okay, so C star is a set of vertices. The size of that is this bar and then C star. Okay, modulus C star means the size of C star, cardinality of C star rather. And cardinality of A means number of edges selected by algorithm. Okay, do you agree with this equation number 1? Not an equation, inequality 1. What it tries to say is that number of elements in optimal vertex cover is either equals to number of edges selected by algorithm, okay, or it would be greater than. Okay, because why? No two edges in A are sharing any endpoint, and C star also must include at least one endpoint of every edge. Okay, so C star is whatever the C star is, whatever the elements of C star is, okay, that must be having. I mean, let's say C star is 1 to 4. Let's say C star is a set of vertices. Let's say it is 1, 2, 5. And A is a set of edges. So, okay. And A is a set of edges. Let's say there are a few number of edges, right? What I try to say is this 1, 2, and 5. Okay, if this 1 is coming here, okay, if 1 is coming here, let's say 1, 3, okay, then it 1 will not come anywhere else because no two are sharing any endpoint. So the second edge would be not having 1, not having 3, would be completely different. So what I am saying is the number of elements in optimal answer and number of edges selected. Okay, and in every edge there will be 2 endpoints. They are disjoint with any other edge endpoints. So can I say that number of elements in optimal vertex cover is this? It should be less than equal to how? Priyank, why? Okay. What is the reason behind that? Optimal has less number of edges. See, two sets are different. First, C star is a set of vertices. A is a set of edges. Okay. We are just comparing numbers, not the set, because they cannot be compared. One is a set of vertices, one is a set of edges. You cannot compare those sets because they are having different things. Okay, but what we compare is the size of the set. Okay, and now I mean, I want to say it can never be less than set of edges in A, because remember, A is also correct vertex cover. the points in A. I mean, A is a set of edges, but if you take all the points in every edge selected by A, that will be also a vertex cover. I'm not saying that it is not a vertex cover. Okay, that is also a vertex cover. C star is also a vertex cover. Okay, but this will never happen. C star less than A will never happen. Okay, why it will never happen less than A? Because otherwise what will happen? uh, yes, any answer? Are you getting what I am saying? Others? Shail, Priyank, Janil, is this inequality clear or not? Or not yet? Not yet. About others? Okay, I'll repeat. Okay, first let me go to the next point first. Then let me come back to again one. Do you agree with this? Do you agree with this second equation? Second is equation that number of elements in approximate vertex cover is 2 times the number of edges selected by the algorithm. Is this clear? Priyank, Janil, Janit? Okay. No, I'm not talking about first. Forget about first, right, for a time being. Second is clear. Harsh, Sail. Harsh is clear. What about Shail? Yes. Priyank? I'll explain that later on, but without example also, is this clear that number of elements in C is 2 times number of edges? Because A is a set of edges and A has 2 endpoints. Sorry, edge has 2 endpoints and both you are including in your answer. So if you have 3 edges selected, then 6 vertices would be there in C. Priyank? Yes, that would be very easy, right? You see. For example, here, how many iterations we have done? First, I selected BC, that is 1 edge. Okay. Then I selected EF, that is second edge. Then I selected DG, that is third edge. So that means I selected 3 edges, BC, EF, and DG. 3 edges I selected, so both endpoints I am including. So B, C, E, F, D, G. So the number of vertices are this 6. The size of C is 6. And what is the size of, what are the number of edges? So edges, if you write, I write it like this. A is equal to BC, EF, and I think it was BC, EF, and DG. So the size of A is 3, and the size of C, C is what? All the vertices like B, C, E, F, D, G. So the size of C is 6, which is 2 into 3. Okay, which is 2 times the size of E. Everybody is clear now? Rishi, Priyank, yes? Can we say on the basis that number of vertices is greater than number of edges for a general graph? Okay. See, Harsh, actually, this algorithm will work for any graph, irrespective of the structure of the graph. So generally, you can have that type of graph. But even if it is not there, still this algorithm will work. Are you getting what I am saying? Yes. Okay. Okay. So second point is clear. Okay. Second point is clear. Okay. And now you see, let me take the first point. Okay. First inequality. First inequality. Let me take the first inequality. What was that? size of optimal vertex cover is greater than or equal to size of A. Okay, let me explain through example first. Okay, we have several examples, so we can have. Okay, okay. What is this C star over here for this graph? You told me, right? C star was, I think you told me B, D, E, right? B, D, E, if I am not wrong. Yes. So the size of C star is 3, right? Size of C star is 3. And what are the number of edges chosen, Priyank? How many edges you have chosen? 3. So 3 greater than equals to 3. True or not? First example, true? Yes. Okay. Let us go to the second example. Okay, this one. What is a C star? C star is just a one vertex, 6. Okay. And how many edges are selected? So the edges would be selected only one, right? So A will be, okay, the set of edges A will be either, there will be one endpoint 6, right? 1, 6 or 5, 6 or that. So size of A is also 1. So size of C star is also 1. So 1 greater than equal to 1, which is also correct. Agree? Second example also, Priyank, Yash? Right. Okay. Third example. Optimal vertex cover is having two, 1 and 3. So the size of, this is C star. Okay. So size of C star is 2. There are 2 elements. And here there will be 2 edges. There are selected 2 edges, right? First time 1, 2, second time 3, 4. So 2 edges. So 2 greater than equals to 2. That is also correct. Okay. And one last example here. Here C star is 2 and the number of edges selected, so the size of C star is 2. Okay. And the number of edges selected is 1. Yes or no? Just a 1 edge selected. Size of C star will be 2 in this case. And the number of edges which are picked, because just a 1 edge will be picked by an algorithm, either 1, 2 or 2, 3. Okay. So size of A will be 1. So now do you agree that size of C star could be A or it could be greater than equal to A? Priyank? Clear? Others? Clear? Yes, I think Harsh was asking. Somebody was confused. Those who were confused in first, Shail, yes, Shail and all, right? Yes. Okay. So what can you conclude from this two? What can you conclude from this two? C star is greater than equal to A and C is 2 times A. Both are correct. Okay. What can you conclude from this? Can I write this in another way? That number of edges selected by algorithm is less than equal to number of vertices in optimal cover. Okay. Okay. And if you replace this, okay, over here, I'll get size of C is 2 times A, but A is less than equal to C star. So I have to put less than equal to 2 times C star, which means size of C is 2 times size of C star, which means if you take a ratio, see, size of C and size of C star both are positive. If I take a ratio, the inequality remains same. Okay, there are no negative things. I'm not dividing by any negative thing. So inequality remains same, so equals to 2. So which means cost of approximate solution and cost of optimal solution. Here the cost means the size, means the vertices. The notion of cost varies from problem to problem, which will be less than equal to 2, which means approximation ratio is less than equal to 2. And hence I proved this theorem, and so it's ratio 2. Of course, I have not assumed any graph, right? You take any graph, give me a counter example Okay. I think, see, Yash, I think you are telling this because you are not clear, or you are still confused with this. Yes or no? Yes. I mean, not about clarity, but still confused that indeed it will work for any or not. Right. So this would be the truth, because in A, every age that you are going to select will be distinct. No two endpoints will match. And in C star, okay, it's an optimal answer. Okay. So, I mean, C star and A both are, so C star is also vertex cover, and vertices of A is also a vertex cover. Both are vertex cover. Just the thing is that, but we have not assumed any graph, Yash. I have taken examples to describe the graph for, yes or no? You see, in the theorem, I didn't mention any graph that take a graph with 4 vertices. My first, I've shown that it can run in polynomial time. That was the first thing. Okay, this is the main objective. Second, I told A is a set of vertices. C star is optimal answer. Size of C is 2 times A, and size of C star is greater than equal to A. Okay, and this I proved, okay, by logical reasons, and this will be true for any graph. Okay, okay, provided you will apply this algorithm, and which means it has a approximation ratio. Okay, others are also getting, uh, Harsh, Rishi, Priyank. Yes or no? Yes. Okay, okay. So this is which way? This is which way? Randomized way. Randomized way, because we select, okay, and the ratio will be less than or equal to 2. You can take a complete graph, you can take any kind of graph, star graph, network graph, complete graph, okay, planar graph, any kind of graph you take and apply this. Okay, these two inequalities or equations will always be followed, and you will get that. Moreover, it will run in polynomial time. So, okay, so I'm just asking you one question. If any problem is given to you, and if you come up with the solution of that, what two things you need to show? What two things you need to show? Yes, of course. If you change the method, yes, greedy, of course, ratio will change. Okay, so I am saying that for this way, the ratio is maximum 2, upper bound is 2. So this is actually good algorithm, because maximum deviation is twice. So if you have optimal answer has the 500 vertices, your approximate answer can have maximum 1000 vertices, not more than that. Okay, so it's like, it's in 2 times the proximity. Okay, my question is, I am asking you, if you devise your own algorithm for some problem, what two things you need to prove? What two things you need to prove? I'm asking you a question so that I can find whether you pay attention or not. All. You find your own method to solve the problem. What two things? I am asking, what two things you need to show? This is for this problem, Urjit. I'm not telling you for it. I'm asking in general for any problem. C and A are the notations, right? Related to this problem. Okay, let's say TSP is given, traveling salesperson problem. Has a factorial time complexity, or which very hard. Okay, you have to try all the combinations. Okay, I need to show two things. The one thing is algorithm runs in polynomial time. That is first thing. Very correct. And the second thing is that proof of ratio that you will get. The upper bound on that ratio, what the ratio can take, maximum value of ratio It's 2 here. It could be something different. And it would be more good if this ratio is a constant like 2, 4, 5, 10, etc. Agree? All of you getting the method? Yes. Okay. Now just pay one more attention. Greedy method that we discussed. Okay, what's the problem with that? Let me give you one example. Okay. So this is your greedy algorithm that you told me. I forget the name, but one student told me, right? So find a vertex V with the maximum degree, add that vertex to the solution, and remove that vertex and all its incident edges from a graph, and repeat this until all edges are covered. This is a greedy, remember, this is not randomized. Greedy way. Because I am greedy in the sense I am choosing a vertex with maximum degree and then I am progressing. How good this algorithm is. So remember, so I am showing you one counter example. I'm not saying this algorithm is bad. This is also good. Most of the time, this algorithm also has a good approximation ratio for most of the inputs. But I am saying that I have one input, okay, where this can take more cost. Okay, that means it can be costly to implement this. Let us see one graph. So can you see this graph in front of you? This is which type of graph? This is which type of graph? Any idea? One set. Yes, it's a bipartite graph. Okay. One student answered this. Yes or no? This is a bipartite graph or not? Yes. Yes. Why? Because there is a one set of vertices over here, another set of vertices over here, and the connections are only from one set to another set. There is no within one set, there is no connection. Within this group, there is no connection. Right. Now you see, if the graph is this, what is an optimal solution? Optimal solution of vertex cover, what would be that? Minimum of one set or second set. So in the first set, you have 6 vertices. In the second set, you have 2 plus 3, 5 plus 6, 11 vertices. So if you take first 6 vertices, won't it cover every edge? Yes or no? If you take the minimum of this 6 and 11, this will be an optimal answer, right? Minimum of 6 and 11. What is 6 and what is 11? 6 is the set of first size of the first set. 11 is the size of the second set. The minimum of that would be 6, right? So that would be my optimal answer, because if I take this vertices, it would cover every edge, because every edge is incident with that. So optimal is this. But if you apply a greedy algorithm, it is sometimes if you are unlucky, because see, there are multiple vertices with degree 3. This is a degree 3 graph, right? Maximum degree, what is the maximum degree of this graph? 3. You see this red vertex, 3 degree. You see this green vertex is 3 degree. So the maximum vertices are, maximum degree vertices are 8. First 6, and from second there are 2 green vertices. So there is a tie. There is a tie or not? In maximum degree vertex, there is a tie. Which one to select? Okay, to break the tie. Anyone arbitrary you can select, but if you select this green one, you will be in trouble. Because if you select a green one, what will happen? You will select this vertex, you will remove these 3 edges, right? And once you remove these 3 edges, the next vertex that would be selected is which one? Again green one, right? Are you getting me or not? Because once you select these edges, the degree of this graph, sorry, green and their maroon, remaining 3 maroon, that is red first on the first set, and green. So again, so first we might choose all green vertices. So if I choose first green and second green like this, then what will happen? The degree of this red vertices will become 2. Then if we select, so then again there is a tie between this red and blue. Again, if we select a blue, okay, 2 plus 3, 5, okay, then the degree of all the above vertices, which was 3 earlier, reduced to 1. And then we have to compulsorily select all the, 6 remaining orange color vertices. Are you getting what I am saying? Yes? Yes. So if you are very unlucky in breaking tie, and if you select first red, all red, sorry, not red, sorry, it is first green and then blue. If you select like that, in green, total 2 vertices, in blue, total 3. So 2 plus 3, 5. So you have to still cover this many edges, this many edges. And for that, all orange vertices should be selected, which are 6. So 2 plus 3 plus 6. So it is 11 vertices you have to choose. The analysis we will see later on, but you see the optimal is 6 and you have 11 if we are very unlucky in breaking ties. Okay, getting this simple example of greedy, this can happen. Just my point is that analysis, I will tell you that this, for this example, the ratio, the approximation ratio can be log of k, that we will see next time, this analysis. It's not a constant factor algorithm. This greedy algorithm for vertex cover is not a constant ratio algorithm, but rather it has a ratio of log of k. That we will see next time. But I think algorithm is clear, right? Greedy and randomized, both algorithms are clear? Yes? Yes, Abhi, Zuzar, are you there? Okay, fine. Yash. Okay, so I hope you understood up to this. Next time we will see the analysis of greedy for the given example, and I will prove that it's not a constant ratio algorithm. Okay, thank you so much. With this, I end.